Hi, everyone. I'm Alyssa Pagan. I'm a science visuals developer from Space Telescope Science Institute within the Office of Public Outreach. And all that means is that I take astronomical data from Hubble, from Webb, and other observatories and create color imagery. And this imagery supports news releases and other outreach products. And just a little bit of my background, I have a background in art and science. So I have a bachelor's degree in art and design from Towson University, and I have a bachelor's degree from the University of Maryland College Park in astronomy, and I use both of those skills in the work that I do. So before we get into how we process the imagery, I think it's important to understand why we process the imagery. And this gives us a little bit of a background of why we make the choices we do. So the first thing is, of course, we want to visualize the data. Numerical information is really important for science research and analysis and discovery. But when it comes to seeing the bigger picture, it's helpful to see an image, just like it's helpful to see a graph to understand that data all at once. And then we want to illustrate the scientific discoveries and concepts, because we want this science to be for everyone, not just for, the scientists. We want everyone to understand this cool discoveries that are happening. And that ties into engaging the public. We want people to be interested in astronomy, and we want to make it more accessible. And so, of course, the first step is actually getting the data. And so the data is actually available to anyone. So if you are interested in playing with the data yourself, you can go to mass.stsci.edu, which is an archive that's hosted by Space Telescope Science Institute, where you can get all the data that you see at webtelescope.org or any of the official NASA releases. If it's not available immediately, it will be available within 6 months. So all this data is public. And you can find data that's fully calibrated as well as the raw data if you're interested. Now, to navigate the archive can get a little bit convoluted, but the easiest thing to do is, if you see a NASA official release image, you can go to webspacetoLescope.org, and under that image, you'll find fast facts or information about that image. So things like the object name, the coordinates, RA and DEC, and this figure here, which is the actual proposal ID, which you can put in to an advanced search within MASS, and it will lead you directly to the data. So it's a very powerful thing. And so just doing sort of an example test with the Pillars of Creation or the Eagle Nebula, we're using the catalog name M16, and we're putting the mission, which is JWST, which refines our search pretty well because Webb is a very new mission. So you're not going to get a whole lot. And then, of course, we're only interested in the NIRCam today. So we're selecting all the 6 filters that we want. And then we're going to click download to put it in our basket. And then we go a step further. We have minimum recommended product selected, because if you don't have this selected, you'll get all the raw data, which you can recalibrate if you want, but that's a whole another thing. So let's just stick to the calibrated data. For this, you only want the I2D FITS file. That's just the image file. So you'll download that here, and it will download as a FITS file, a compressed zip file. Now, important to know, these are very large files because they're mosaic, so they're, a few gigabytes, just to warn you when dealing with them. Okay, now once we have our calibrated data, then we start doing something called image stretching. So this is actually an image of the Webb Deep Field in the 2.7 micron filter. This is how all images pretty much start out in visualization software. So it looks dark. It looks like we've messed up, but there is information there. It's just all hidden sort of on the black end. So if you look at our histogram distribution, or our distribution of pixel values, you can see that all our pixel values are like on the left where the black is. What we want to do is we want to stretch that distribution out so we can see all of the faint details, and we can do that a couple of ways. This is just an example using a 2-bit image of a parrot. So the first example is this, not doing anything. This is just linear 1-to-1. And then in the middle is a linear stretch or linear transformation, where we're trying to bring up the brighter values, but in doing so, we're actually losing them. So the top 3 brightest values all get sort of lost together. We don't want to do that. So what we want to do for our astro images is do something called a nonlinear stretch. So we're bringing out those bright values, but we can differentiate between all of them at the same time. So we're maintaining it. So this is an example of a linear stretch, something that we don't want to do on the same image of the Webb Deep Field. You can see we're bringing out those fainter values, which is great, but we're completely clipping the brightest regions. We don't want to do that because we're losing information. So again, we do a nonlinear stretch. Again, we're stretching out this histogram. We're bringing out those beautiful faint details, but we're maintaining the details in the brightest regions. So that's exactly what we want to do. And we want to apply that to all of our images in each filter. So this is just another example using a FITS Liberator, which is a free software. If you want to liberate your images and convert them into TIFFs, you can do that using this software. There's other software that you can use. This one's free. Okay, so let's look at an example with the pillars again. So this is linear. This is all of the filters that we have. So this is just straight from the telescope before we applied any stretch. And then now we're bringing out the details in all these different filters, all 6 of them. So that's what we want to do first before we start assigning color. Now, something that's important to note is that these individual filters, depending on whether they fall on the short wavelength channel or the long wavelength channel, they might have a different scale because they have different chips, and that makes it more high resolution than the other. So the short wavelength channel has more resolution. So it'd actually be 2 times larger. And so you'd want to rescale them once you get the data. So you can either rescale the 4.4 or the longer wavelength channels by a factor of 2 to match the shorter wavelength channels, or vice versa. You can reduce it by half if you know you're having problems with your memory and RAM. And they should be aligned based on the calibration pipeline, but whatever photo editing software you're using, or if you're using some sort of astrophotography software, you might have to tweak them in the alignment a little bit. It really depends. And then, of course, before we apply color, there's something that we have to do in terms of correcting artifacts. And so you can see there's some banding errors. There's some black cores of stars, and we know they don't look like that. This is just something that's introduced by the electronics, the cameras, and the pipeline. So we just have to remove those because that's not actually what we'd see in the sky. And then we've cleaned up the image individually for each filter. Okay, so now we've done the image stretching. Now we can start assigning color. And so this is an example of how the mid-infrared instrument or the MIRI instrument is collecting light. So the light is being redirected into the instrument, where then it goes through specific wavelengths or a filter wheel. And that's how we assign color, because we're collecting light in specific wavelengths. And then we assign color appropriately to those filters. But how do we do that when we're working in infrared? So we use the same physical meaning, or how we see light invisible, and we apply that to the infrared, meaning the shorter wavelengths in visible light we perceive as blue, and the longer wavelengths we perceive as red. So we use that same mapping and apply that to the infrared. So now that the infrared filters that we get that are shorter, we apply that as blue, and then the longer get applied as red, and so on. So you can see here, after we stretched all of our images in the pillars, then we can assign colors in what we call chromatic order. So again, the shortest wavelength filters, in this case, it's the 0.9 micron filters, gets the purple, and then we move on to the blue, the cyan, the yellow, the orange, and finally the red for the 4.7 micron filter. And then we can combine that all additively to get our full color image. But now we have to consider more of the aesthetics. Now, there's not one point where this goes from subjective to objective or vice versa. We're kind of weighing both the art and science all the time. And we're thinking about the science story as well as the filters and the aesthetics. So in this case, we're thinking of clarity in terms of like the actual details in each filter, which we can emphasize, of course, in sort of contrast and color, but we're also thinking about the clarity of the science message we're trying to tell. And of course, at the end, it's the composition, what creates the best sort of aesthetically pleasing, compelling image, but also conveys the science the best as well. And so this is our initial color composite before we sort of made any sort of aesthetic adjustments or any sort of color balancing or white balancing. But that's what we have to do in the next step. So here is sort of us transitioning, creating more contrast between these filters, bringing out the dust, which is sort of represented in these redder orangey colors, and then separating that from the gas. We're trying to create some depth here, and we push that a little bit further, really enhancing that contrast to really showcase those different physical phenomenon that's happening here. And once we get it to a stage where we like, sometimes it can be very helpful to extract the stars only momentarily so we can work on the background separately from the stars, because we don't want to change anything about the stars. They're very bright. And if we start changing things about the background to bring out sort of the details, the faint details, we might saturate the star. So it's easier to do it this way. And sometimes we can actually see some more artifacts that we didn't see before because the stars were masking them. So we can see sort of some seams here. It's kind of hard to see where there's different tiles that were stitched together to create the mosaic. So we want to fix that. And so now we fix that here, and we can put the stars back in. Now, once we have the full color composite, sometimes it's easier to make the slight changes and remove some of the artifacts then, like cosmic rays, because you can see them very brightly in the different color images, and it will only appear in one of the filters. So it's very easy to sort of, sample a region of the dark sky near it and replace it with its nearest neighbor of good pixels. And so I was just talking about pillars of creation, was a star forming region. It has 6 different filters, but this is not a one size fits all. This is where creativity really comes together, and you'll find different processes and techniques depending on the image you get. So we have the Tarantula Nebula, the Deep Field, we have Neptune, and we have this protostar region. So each of them had like a different approach, depending on how many filters there were, depending on what information we're trying to show, and etc. And so this was just a brief overview of how we create color imagery, but you can learn more at the URL below, which also has videos that you can also check out. So thank you everyone for listening, and I hope you have a great time at the rest of the conference.